will be the Quark model for the F shell.
Well, I first met, or made contact, I should say, with Hugo in around 1960. Hugo had written to David Judd at the Lawrence Radiation Lab, as it was then, and he asked him a question about some recoupling coefficients. David thought that maybe I should answer, so in fact, perhaps the letter should have come to me in the first place. But anyway, I answered Hugo with a long letter full of formulas, and it disappeared into a black hole. Years later, we entertained him at Hopkins, and he gave a series of lectures. And this was at the time of the Chernobyl crisis, and he was very vociferous on that matter, as you can perhaps imagine. I remember him saying that the director of a nuclear plant should be like the captain of a ship. And we all agreed, of course. This was a time of great concern to him. Well, today I want to talk about some aspects of something we've been working on for the last, I suppose, 12 years. And the title I have here is simply Development in the Quark Model of the F-shell. And I've included my last postdoc, Edwin Lowe, because he did a lot of the technical work on what I'm going to speak about today. He's my last postdoc, perhaps he's my final postdoc. But he was very helpful. And I thought I'd start off with, in fact, a summary so that you can see where I'm going. I realize that many of you do not have Lie groups at your fingertips, and so this is going to be very much of an overview, but I thought if I started with a summary, you could at least see where I'm trying to go. Now, the motivation stems from Racker's 1949 paper dealing with the Coulomb energies of the LS terms of the configuration Fn, that is n equivalent F electrons. The problem with these configurations is if you say I have a doublet p term, it often doesn't define the term because there could be 6 doublet p terms. How do you get around that? Racker had a very ingenious way. He said, well, think about the rotations, think of the 7 orbital functions, forget the spin, of an F electron, and consider rotations in that 7-dimensional space. Because you will stay within these configurations, you're going to get irreduced representations, and you can use these irreduced representations of this group to help you separate these terms. He also found that there was an intermediate group between this and the regular rotation group, which is defined just by the angular momentum quantum number, capital L. This group is one of the 5 exceptional Lie groups, labeled G2 by Cartan in, I think, 1894. So I'll just go through that in a little more detail in a moment. And then I want to tell you what quasispin is and show it explains some of, no, I have to say, the puzzling selection rules. What Racker found was that when you apply the Wigner-Eckart theorem to these groups, SO7 and G2, the Wigner-Eckart theorem works better than it ought to. So I have to say what that is. But then I have to introduce quasispin to tell you that all of the puzzles related to SO7 disappear if you introduce quasispin, but not the puzzles for G2. Then I want to mention this remarkable 1937 paper by Sugarman. This paper appeared in the Journal of the Franklin Institute of Philadelphia. And if you pull the volume from the shelf and look at it, there are articles on toothpaste, forestry, what to do with pine cones in the winter, and so on. But buried in that is this statement by Sugarman that when you are calculating the terms in a complicated configuration like Fn, and by the way, Sugarman goes up to I to the nth. The way to do it is not to start listing all the Slater determinants and seeing what you've got. It's in fact to separate the electrons according to their spin orientation. So you put the spin-up electrons on one side, the spin-down electrons on the other, and you only apply the parallel exclusion principle to these groups separately. And then you just couple them together. In other words, you don't antisymmetrize with respect to all the electrons. And that way, you can couple these independent objects and count the terms like lightning. As I say, it goes up to I to the nth. It's just fantastic. Well, one of the things we noticed was that, in fact, you can factor both these parts again into two parts. And these two objects, now which make up the spin up, and another two objects, similar objects that make the spin down, we call quarks. Now, that doesn't mean we can publish papers in which we use the word quark. You submit something to the Phys.Rev letters, and they say, no, quarks, you can't call them quarks. Because it might confuse people. Now, this assumes that everyone has a level of intellect of 5-year-old children, I would think. But nevertheless, the rules are the rules. And in the first, we have managed only to get two Phys.Rev letters. In the first one, we managed to sneak in the expression quark-like. That was as far as they would let us go. And in the second one, which came out a couple of years ago, when we completed basically the analysis I'm going to talk about today, we couldn't use quark at all. One of the referees suggested that instead of the word quark, we should use Schudmanian Bogolon. Schudmanian in honor, of course, of the first factorizer, and Bogolon in recognition of Bogolyubov and his contribution to physics. Even Mr. Bazbaz, the kind editor, was, I think, taken aback by this suggestion. So we didn't have to take that route. Now, the quarks, in fact, have an angular momentum structure. The quark has dimension 8, but it comprises an angular momentum, an orbital angular momentum of 3 units and an angular momentum of 0 units. You take 4 of these, couple them, they're completely independent, work out all the L values, you get all the L values in the FN shell. All 2 to the 14 of them, all those states. Provided you put in 2 parity labels. We have to say whether they're an even or odd number of electrons in these spaces. So here we are with these quarks, F plus S. And again, I like the notation that you can get away with. In fact, are encouraged to use in the Institute of Physics journals, where they like Roman for spectroscopic labels. This enables us to use italics for quarks. And it's a bit confusing because we've got an F quark and an F electron in this game. Again, Physical Review letters, they don't accept that. All these have to be italics. So what do you do with these? Well, we use italics too. We're not going to oppose directly the... you might say, why do we publish in Phys.Rev letters? In fact, if it wasn't for this postdoc, I don't think I would have done. I think I'd have given up. But, you know, there is a kind of prestige value, although well, I'm not quite sure what we get for it. But anyway, so this is our notation. So I'm nearly at the end of the summary. And the last point I have to make is that when we change the phase between the F and the S quarks, we can do this by just replacing... You see, we're going to take these quarks seriously. They have creation operators, annihilation operators. We're going to replace a creation or an annihilation operator by minus that. When we do that, we find that for the fourth quark, the sum of the spin and the quasispin is left invariant, and this gives us a complete explanation of all of Racker's surprising results. So that was very, very striking, and I hope to have Oh yeah, I think I shall have time. I see I'm not going to go into any detail really. But we have limited success, and so there seems to be a future. Okay, so that's what I'm going to talk about. Now, everything I speak about today has to do with the Coulomb interaction. The Coulomb interaction between the F electrons. Well, you'll all be happy to see this transparency I've taken from Jackson's electromagnetic theory that, of course, we all use and batter our students with over the years. This is from the first edition. This is before he started putting epsilon zeros everywhere. And in fact, the early editions, the first edition is so much better, in my opinion, because you see a man struggling to do it and do it right. He's not concerned about the gloss. You look at the later editions; they've been fancied up. They look nicer, but they're just as, in fact, a little more difficult to understand sometimes. So this is 1 divided by R12, the distance between two points at coordinates x and x prime. Now he talks about this double sum, but in fact the sum over m, all you're doing here is forming a scalar product. It has to be scalar because this distance, if you rotate it, is an invariant if you rotate your coordinate frame. So this is just a dot product, and spectroscopists, in Racah in particular, would write that expansion in this way. He'd have some Slater integrals which take care of integration over the radial part of the F electron. The angular parts now are in these renormalized spherical harmonics. They're written just as dot products for electron I and electron J. So this is Slater. What Racah said was, we're going to use these groups. We're not interested in these separate products don't have very nice properties with respect to these other groups. Why don't we take linear combinations of these dot products? So now he's got 4 linear combinations and 4 linear combinations of Slater integrals. So it's the same problem, but he can give labels to these representations of SO7 first, three numbers, G2, and 2 numbers. Now, chemists use this scheme. They're totally familiar with these group labels, even though they might not understand what they mean. And this is because they use these complicated codes to fit their data. They're just A, B, C, D. It's just a label. But I'd like to say just a little bit more about where those labels come from. And to do that, I'd just like to say that, or remind you, that when we're dealing with a rotation group in 3 dimensions, and this is illustrated for the 7 states of an F electron, we have a shift operator which will take you from an m of 1 to an m of 2, or we have a shift down operator which will take you in the opposite direction. And that little distance there is meant to be the same as the distance here. So you can superpose this and see what's going to happen. LZ simply tells you where you are. This is called weight space, and this weight space is one-dimensional. If we're working for the rotation group in 3 dimensions, we're working with a one-dimensional weight space. However, for G2, we're in a 2-dimensional weight space. You don't have to worry about the upper figure. This is the important figure. So we have 12 shift operators that can take you now in a plane. And these shift operators each correspond to a different generator of the group. They're the analogues of the shift operators. In fact, if superposed on a weight diagram, they will take you from one weight to another. And there are 12 of them. However, there are 2, because there are 2 coordinates, there are 2 more operators, making 14 in all. And this representation, to which the generators belong, is 14-dimensional. It's labeled by the highest weight. Now, Racah used a very clever scheme in which in which he used a coordinate, an oblique reference frame, taking one axis along here and another axis along here, and this has the coordinate 1, 1. And this is how Racah would label that irreduced representation. He called it 1, 1. Now, finally, I can touch bases with Ugo by reproducing the Wigner-Eckardt theorem for SO3 in the form that Ugo and Fano give it. The story I heard about this book is that Fano basically wrote it, and he'd send stuff to Racah, and Racah would say, oh, that looks all right. Fine. So that was that chapter. Then he'd send him another chapter. Yeah, Racah would say, yeah, that looks all right. So, in fact, and basically it does look all right. But it's a little bit odd. These Gothic symbols for tensors. And these two forms, I must admit, I prefer the form in which, given in Edmund's book, where the 3J symbol has the upper row in the order of the symbols on the left, J, K, J prime. But what this formula does is it pulls out the dependence on the so-called magnetic quantum numbers, the M's. But this, actually, by having a different symbol here, this is something which a lot of people don't bother to do. They use the same symbol. Racah realized, and so, of course, so did Fano, with this weird notation, that it's not the same thing here as here. You haven't just put double bars around something. And some people think that because two tensors are identical, their reduced matrix elements are identical. And that is not always true. People write to me and they say, well, I've got a factor square root of 2s plus 1. Where did that come from? And I know immediately that they've misapplied the Wigner-Eckardt theorem for a double tensor, which you have to know which spaces you're reducing it with respect to. It's fine if you're just working in one space and you're reducing with respect to one angular momentum. As soon as you get two or more, then if some of the ranks are scalar in these additional spaces, but yet the reduced mechanism are reduced in those spaces, you can come up with mistakes. Well, I should say this is the Wigner-Eckardt theorem for SO3, but for SO7 and for G2 it's more complicated. And why is that? If you take the Kronecker product of K with J, you find that J will appear not at all or once. It will never appear twice. Put it another way, if I have a p electron and I couple it to another p electron, I get a d state. I don't get two d states. I get one p state, not two p states, and just one s state. But with these other groups, which are not simply reducible, you can get representations more than once. And when you do that, you have, in fact, two. Supposing it occurs, this situation where it occurs twice, you get, in fact, this plus another term looking like this, with another 3J symbol, generalized 3J symbol, and another generalized reduced matrix element. Well, this is Racah's famous paper. What an abstract. The calculations of the coefficients of fractional parents and the energy of matrices through the configurations of F, and you simplify very much by the use of the theory of groups. Tables of results are given. He was doing it. It represents an almost unbelievable amount of work. And not only that, but there's only, as far as I know, one numerical error in the entire paper. It's full of numbers. And those are the days when, of course, every number was not on a disk or anything. You had to do it, and the printer had to get it right. There's a 71 somewhere in this article. It should be a 72. But actually, as soon as you see 71, you should say, this looks fishy to me. Because all the numbers in this game are nice numbers. If you get any high prime, you say to yourself, I better check this. So in fact, you don't have to worry. In 1965, Wyburn wrote a very useful book on the rare earths, in which he used Racah's classification to do all the states up to the half-filled shell. Now, this is to give you just an impression of the size of half the shell. Of course, the other half is the same as this. But I want to just magnify the top left-hand corner and just look at that so we can see what's going on. So that's just the top corner. If I have one electron, its spectroscopic level is doublet F. It belongs to the 7-dimensional irreducible representation 1, 0 of G2 and the 7-dimensional irreducible representation 1, 0, 0 of SO7. Because, in fact, for SO7, the weight space is 3-dimensional. You need 3 numbers. Well, for 1 and 2 electrons, these labels don't add very much because this classification is complete. But when you get to 3, you'll notice there are two doublet Fs. But they can be separated by SO7. One belongs to 2, 1, 0, the other 1, 0, 0. This is not a physical separation. If you look at what would be a triply positive neodymium ion, you will not find these doublet Fs with these labels existing in nature. But it's a basis within which you can perform a calculation. Now you'll notice that SO7 by itself is not enough to separate the doublet Ds. But in fact, although the W classification, the SO7 is not enough, the G2 classification steps in and these two labels, did I say doublet D or doublet G? It separates the doublet Ds and it separates the doublet Gs. In fact, it makes a complete separation. It just works fine. It works fine for F4. For F5, there are a few duplications, but one can cope with those, or rather, Racah could cope with those in a fairly straightforward way. Let's get back to Racah's paper. You see, Racah's going to now apply the Wigner-Eckart theorem to SO7. And he needs to know if he's going to take a matrix element between different W's, and he's going to do it for E3, that's the Coulomb operator that belongs to 2, 2, 0. He needs to know how many times, if I form the Kronecker product of W and W prime, 2, 2, 2 occurs in it. If it occurs only once, he just can use the Wigner-Eckart theorem in a very simple form, just as if it was at SO3. Of course, you have to use different Klebsch and coefficients, but it goes through without difficulty. But in fact, it often occurs more than that. And he was very much surprised to find that if he added to the Coulomb operator another, this is an operator whose eigenvalues he could easily calculate. It's related to Casimir's operator for SO7. Its eigenvalues are known. You can subtract that off any time to find out what the matrix elements of E3 are. But he's getting all these proportionalities. He's getting some zeros here. He's defining the very simple, just depend on n, particle, electron number, and seniority. And there's some more relations. And these were very surprising. And he says the fact that these depend on are connected with the properties of the symplectic group, which leaves invariant, a form he's given elsewhere. The investigation of these properties is beyond the scope of this paper. Now, as I said at the beginning, all of these can be understood if you introduce the notion of quasispin. What is quasispin? It's not difficult at all. It's an angular momentum. The shift-up operator creates 2 electrons in a singlet S state. The shift-down operator annihilates 2 electrons in the singlet S state. And QZ leaves you with the same number of electrons and basically counts them. The eigenvalue of QZ is directly related to n. But because of 2n, this property of 2l plus 1 minus n is symmetric about the half-filled shell. The quasispin itself is related to Racah's seniority. So when Racah was using seniority, he could have used, in fact, you might say he should have used quasispin. And I've given an example here. If you look at there's a triplet P term that occurs in the configuration F squared. Here it is. Its MQ is minus 5/2. If I add to that term a couple of electrons coupled to singlet S, I'm going to get another triplet P with the same seniority. And I can add another one, another one, another one, until I get up to F12, and when I try to add two more, I get 0. So here I have a quasi-spin multiplet with a Q of 5/2. Here, I've given a simpler case. Here's a term doublet H of seniority 5. It first appears in F5. It will reappear in F7 and in F9. The quasi-spin corresponding to the seniority 5 is 1. And when you work out what quasi-spin does, all of these relations that so puzzled Racker become ludicrously simple. What about these zeros? What Racker has done, although he didn't know it, he's created an operator with a quasi-spin rank of 2. Now, something with seniority 7 only exists in the middle of the shell. It has a quasi-spin rank of 0. If you try and calculate the matrix elements of a tensor of rank 2 between Bra and Ket with angular momentum of 0, you're going to get 0. It's the same reason that a quadrupole moment doesn't exist for a nucleus with a spin of 0. And here for 6, a spin of half. So this becomes trivial. And these things are simply the ratios of Clebsch-Gordan coefficients in quasi-spin space. So that basically took care of a lot of the puzzles. However, in Racker's paper, we find more mysteries with respect to G2. So he again found a very simple factorization. The calculations show that when this multiplicity exists, that is the number of times you take the product of the two irreducible representations of G2 that exists in the Bra and the Ket, 2,2 is the label for the operator. When 2,2 occurs more than once, you would expect a linear combination of more than one term. But in fact, always you get just one. Yes? 5 minutes. Okay, I'm glad I gave a summary. Now, this is the thing that the quark model solves. And I have to be a little brief here, but it's easiest to understand the quarks if I work with the d shell. So let's take an even number of d electrons with their spins pointing up. With no d electrons, I have a singlet S state. If I have two d electrons and their spins pointing up, I get a triplet F and a triplet P. If I have 4 with their spins pointing up, I get a quintet D, but that's it. I've got the half-filled shell. So I have this sequence of angular momenta, S, P, D, and F. And the quark model says, let's take this seriously and find these angular momenta by coupling two quarks of spin 3/2. Because if you take 3/2 with 3/2, you will get these. For the G shell, the quarks have to be D plus H. And I've already said that for the F shell, the quarks have to be 3 and 0, and F plus S. Because the dimensions of the quarks, F plus S has dimension 8, it's natural to consider the rotation group in 8 dimensions and take SO7 as a subgroup. What I've done here, I've carefully plotted out a 4-dimensional cube and projected it onto a 2-dimensional surface. So this is a half, a half, a half, a half, a half. This is a half, a half, a half, minus a half, and so on. And on that, again, I've carefully projected. I had to choose the direction so these things didn't overlap. The 24 generators of SO8. Now, 4-dimensional space is very interesting because of its extraordinary symmetry. In this upper figure, I've got the four-dimensional cube again, and it has 16 vertices. But if I take one of these vertices and find, with those arrows on the previous transparency, what other vertices I could arrive at by making little trips, I don't get all of them. I just get a collection of 8. On the other hand, if I take this and do it, then in fact I get another 8. Finally, if instead of taking a four-dimensional cube with coordinates plus or minus a half, 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 I simply take points on the axes 1, 0, 0, 0, minus 1, 0, 0, 0, and so on, I get 8 points again, and they'll come out here. Now, the remarkable thing is that each of these arrays of dots, heavy dots, can be rotated into the other. If you try and do this in three-dimensional space, you'll get a tetrahedron here, and an octahedron here. So they'll be different. But in four-dimensional space, they're the same. And that threefold, now of course I don't have time to go into details, but that special symmetry we interpret as being connected with the three SO7 groups that one can take as a subgroup. One of those SO7s is Racker's. And when we use, in all seriousness, the generators of Racker's group, but using quarks, we find we get these, get a tensor of rank, these are quark now, 1, 5, and 3. However, we can get another SO7 group by changing the sign of the S quark. And it's very easy, or at least not difficult, to pass from one to the other. And as I said at the beginning, S plus Q is invariant, I kind of have no time to show this, under that transformation. I can give you an example of a transformation. Here is a state. This is a W representation, and alpha denotes a total spin T, a projection MT, an angular momentum L, and the representation 30 G2. When you take just the fourth quark and do that flip, S going to minus S, you find that it can be expressed as a linear combination of representations of these other SO7 group with very simple coefficients. We can also find that that combination E3 plus omega is an invariant. And in this way, we can get relations between the matrix elements of this operator in the two schemes. Now we simply take the double primes off and say, how do we know whether they really have double primes or not? It's just an SO7 group. So we interpret the matrix elements, the new ones with the SO7 double prime labels, in terms of unprimed symbols. And so we get a whole lot of equations. An outcome, what do I say here? Well, this goes into a little detail about how to manipulate the operators. And we find that, in fact, we can produce all of Racker's exceptional and puzzling connections. This is our latest PhysRev letter. You see, instead of having from the quark model of the F shell, we had to say from automorphisms of SO8, which seems a little more remote to me, unless, but anyway, I guess if you're a group theorist, maybe that pulls you in. I don't really have time to say more than say that we're working on other operators, in particular the spin other orbit. My colleague in Amsterdam, Jorn Hansen, has worked out the matrix elements in the F shell of all the group theoretical components of this interaction of the spin of one electron with the orbit of another. It's a magnetic type interaction. This is more complicated because the spin and orbital ranks of the operator are 1 and not 0. So you're not dealing with scalars as you are in the Coulomb case. And we get we've had some success. This is the last page of that phys.rev letter. And here's a whole bunch of equations for a particular component. So that come from replacing s by minus s in the fourth quark. So we've made progress, but we don't get them all. So maybe the third SO7 group has to be brought in, but that's going to be much more difficult, I think. Thank you.